Yes, and I will
Cool.
mute.
Nice. All right, well, hello, my name's Daniel. I'm part of the Exatrix collaboration working at Berkeley Lab. And today I'm going to talk about using graph neural networks and other machine learning for track finding. So the Exatrix project or collaboration aims to study the performance of machine learning approaches for exascale tracking problems, hopefully to get to the point of production level tracking on next generation detector systems. So specifically, I'm going to focus on the high luminosity LHC event data. So the goal here is that we take from the starting point that graphs are a natural way of representing tracks. And so we're going to look at using learned embeddings and graph neural networks to process high luminosity LHC data in under a second into triplets, which we'll call seeds, which can be used for further processing with traditional techniques, for example, combinatorial Kalman filters, or even to process into tracks, so assigning each hit to exactly one track. So this is the overview of the pipeline that we use. I'll come back to this and explain each section, but in general terms, we take in raw data, which is embedded into some learned embedding at latent space. We filter those learned embeddings into a graph, which is then fed into a GNN, which is trained and classifies the graph into doublets. And then we convert this into a triplet graph, which contains, we hope, even more accuracy and information, which is trained and classified. And then eventually we can use those triplets for either seeds or to cluster into tracks. So I'll just mention that the Exatrix project has explored many different machine learning approaches to this in the past, when it was called the Heptrix project as well, using convolutional neural nets, treating the tracks as images, or treating the tracks as sequences of points, so using long short-term memory. The issue here is that the scaling with the number of tracks was quite poor. And so the concept was to use graphs as a natural representation. So the data set that the graphs are being applied to comes from the TrackML Kaggle competition. So if you're not familiar with this, this is a simulated set of 9,000 events, many of which we train on, and then a small portion is left for testing and validation. Each of these events has around 100,000 hits from around 10,000 tracks. Hits from the same track can occur multiple times on the same layer, which we call duplicates. And there are hits present that don't belong to any track, which we call noise. So this is an image of the detector. We are going to focus on the central area of the detector called the barrel. And the idea is to classify each hit into a track. And the way of measuring the success of this is with something called the TrackML score, a number between 0 and 1, where ideally if you assign all of the hits that belong to the same track to a certain category, a number, an integer, then you get a TrackML score of 1. For simplicity and to treat this as a form of toy case, we're going to focus on the barrel and ignore noise. So given that we have the coordinates and hardware information of each of these hits, we need to construct them into some sort of graph, which is to say nodes and edges. In the past, we've used geometry. For example, we could place a maximum bound on the pseudo rapidity and the azimuthal angle of any connection between the two hits. And this has worked fine as a starting place, 45% efficiency, around 5% purity. But now we use a learned embedding space to construct the hits. I'm not going to give so much detail about this. If you're interested, and you should be, I suggest you tune into Nick Choma's talk in half an hour after my talk is finished. which will go into the embeddings that we use. But in general terms, we take each hit in the event, embed it into some n-dimensional space using the features of the detector. We associate hits from the same tracks as close with some metric in n-dimensional distance. We then use another multi-layer perceptron to score each target hit against the seed hit of that neighborhood. And then we filter out using that MLP what we call doublets that pass this score threshold. And all the doublets that pass some arbitrary threshold we use to generate a graph. I will just note that we apply an ordering of the layers to make it a directed graph, and we also apply a layer adjacency condition. So this will come back to haunt us shortly, but we will not accept doublets that skip a layer at this point, but that's something that we're investigating. It's also worth noting that the graphs that we're constructing don't fit on a single GPU. So we need to, in some way, segment the graphs. And there are several different choices on how exactly you want to make that cut. And I will just say that some of them lead to faster processing and lower memory, or better efficiency and accuracy. So this is one parameter we can tune. So a graph neural network is a sort of generalization of a convolutional neural network to arbitrary connections between neighbors. So we have a graph here, for example, where we want to classify each edge as either real or fake by placing some cut between 0 and 1 on the score of each edge. The paradigm we're going to use is called message passing. And this is basically allowing each node to become aware of the features of its neighbors through each shared edge. And then we iterate this message around a graph, which enables nodes to learn information from far away in the graph, depending on how many iterations we use. So as I said, this is the message passing formalism. You can extend this formalism with an attention mechanism, which was pioneered in this work and others around this time, where basically each edge is also given a neural network. And then the weighting of each edge allows each node to learn which of its edges it should pay attention to. And then we iterate around this message passing attention loop through the network. There are some extensions to this paradigm that you can add. For example, we can add residuals so that information is preserved between iterations, and this stops important information being washed out by the message passing. We can also make the network smaller and simpler by using the same network n times and using a recursive mechanism. But we found that the best efficiency and purity comes from this residual attention mechanism. That's not to say that it's the smallest network or the fastest. That's at this stage probably the vanilla message passing, but this has given some of the best efficiency and purity that we've seen. So those values are very good, actually. So we have to place some arbitrary threshold on what we call true and fake. So given a threshold of 0.5, we find a doublet purity of 91% and efficiency of 95%. And then those values are more or less flipped for a threshold of 0.8. So this is an efficiency and purity against the actual data being fed into the GNN. So that's constructed with the learned embedding. And that learned embedding already has a very high efficiency. It's finding 96% of the possible true doublets in the data set, which, as I said, is much higher than the previous geometric cuts we were placing. But that said, these metrics are not the end. We use these doublets and their scores to create triplets without losing any efficiency. And the triplets are hopefully perform better than the doublets because you would hypothesize that they have access to curvature information. So we hope that the accuracy is better. The doublets graph is converted to a triplet graph in order to use the same graph neural network formalism. So we do this by concatenating nodes together into doublets and then keeping the score from the doublet GNN as a feature input into those nodes. You might complain that the size of this graph is going to explode, and naively that's true. If we have 6,000 tracks in the barrel, 40,000 hits, that creates about 140,000 doublets, 400,000 triplets. The scaling is poor. But we can be a little bit sneaky and place a very small cut on the doublets coming out of the doublet GNN and retain still a very high efficiency. And after this cut, the number of doublets and triplets drops quite dramatically because we've basically classified a whole lot of easy fake doublets and removed them from the graph. So in this way, if we want, we can then continue this process to a quadruplet GNN, a quintuplet GNN, with cuts in between each, and the size does not snowball. And I will just mention that we use a very fast doublet to triplet graph conversion method using sparse adjacency matrices on a GPU. So this gets extremely good performance that we're actually going to include in the latest PyTorch geometric release. We can see the improvement in the performance over the doublet GNN. And of course, we would expect an improvement because the triplet GNN is using the scores of the doublet GNN as well as information. We have an efficiency of and purity of around 99% for the triplet GNN. Again, I'll just point out that those efficiencies are relative to the graph data that's fed in the first place, not the raw event. We can see that here we have gold is a correctly classified doublet from the triplet GNN. Most of the mislabeled triplets live in the center of the detector, as you would expect, because the occupancy there is quite high. And this could be an argument that if we use triplets as seeds, we could seed only from the outer layers because our confidence there is much better. And here we see all the black lines of the triplet detector, triplet GNN, where the triplet GNN has outperformed the doublet GNN. So it outperforms quite a bit and goes back and fixes a lot of the mislabeled doublet GNN edges. So I'll just give some general performance measures. I won't go too quantitative into the current benchmarks in detectors. You can look over those yourself, but I will just mention that our seeding efficiency and purity is certainly competitive. So above 0.5 PT, 0.5 GeV, we have a seed efficiency over 90%, and that's relative to the actual event. So the denominator there is all possible true triplets in the event. And our purity is extremely competitive, 99%. So I have amended one of the CMS benchmark plots with our false positive, true positive rate. And it is, as I say, very competitive. And this is a pileup of 200. This is looking towards a high luminosity LHC. The inference time is around 5 seconds per event per GPU. This is split pretty evenly between the embedding construction stage and the two GNN stages. And there are certainly many optimizations that we're looking at making there. So I'll move on to the track labeling section. So the goal here is that given a doublet or triplet graph, we want to use those edge scores to group together nodes into tracks. So the pipeline is essentially exactly the same until the final section, where instead of applying some cut and getting a collection of seeds. We feed the output of the triplet GNN into some sort of clustering algorithm. We use here a dbScan, which typically takes points and calculates a distance metric on those points and then clusters them based on density. But we want to use dbScan's recent update that can take in sparse methods, and we want to apply that to our graph representation. So it takes a bit of fiddling. What we do is take the edge scores that are output by the triplet GNN and subtract them from 1, which basically associates nodes that are likely to belong to the same track as having a very small distance away from each other in the graph. Then we feed those distances as a pre-computed sparse matrix and call that the metric of dbScan. And I just want to note that we changed our directed graph to an undirected graph to improve the performance of dbScan, if you want to try it at home. So dbScan works actually very well on sparse graphs. So here are some general benchmarks that we have constructed. So basically take a truth graph of an event where we connect all hits together that belong to the same track and give them a score of 1. We add in randomly connected hits that don't belong to the same track, give them a score of 0. We call this the ideal graph or the truth graph. And then we can randomly mislabel those edges. So if we want to reduce efficiency, we can mislabel true edges. And if we want to reduce purity, we can mislabel fake edges. And we can see that dbScan, here we have the TrackML score on the y-axis. So a TrackML score of 1 implies a correctly labeled graph. dbScan has a linear reduction in TrackML score when efficiency reduces and an exponential reduction in TrackML score against purity. So this is maybe a cautionary tale that to use dbScan in these situations, the purity has to be extremely good, but it can suffer a small efficiency hit and still perform quite well. So I'll give some early results from this technique. So applying dbScan to the full truth graph of an actual TrackML event, we get a very high TrackML score. So this is the absolute best that could be produced with dbScan. Using the requirement that layers, only adjacent layer hits can be connected, we get a somewhat lower score. So this is the absolute best that could be obtained with our formalism. Then we skip to an actual constructed event. So this is the event constructed with the learned embedding. So we do take a hit right off the bat because the learned embedding has some less lack of efficiency of 96%. But this is something that we are working on bumping up. So again, this value is the absolute best we can do on these particular graphs. And then in real terms, the dbScan applied to the doublet GNN predictions gives us a TrackML score of 0.8. This is not competitive. I mean, the winning score of the TrackML challenge was over 0.92. So we need to do better than this. Once we convert to triplets, we immediately take another hit. There are some sort of doublets that are being lost in the conversion. So the best we can do on truth is 0.84, and realistically we get 0.815 with the triplet GNN. So that's a lot of different numbers, but the takeaway here is that we have 2 big hits to our TrackML score. There is a loss from the embedding efficiency, and there is a loss from doublets that are being lost in the conversion. So I'll just quickly mention where those doublets are. They are on the end of the barrel, which makes sense. A lot of the doublets are heading out of the barrel and into the end caps, which we don't consider. And a lot of them are on the edge of segments. Remember, we had to divide our graph into sections, and when tracks cross those sections, we lose potential triplets. So some solutions there are to stitch up our graphs again between the doublet and triplet stage, that helps a lot, and in fact improves memory usage quite a lot, so that we are not duplicating doublets between the segments. You can see a slight shadow here, which is all the duplicated edges that we remove. And we also choose to ignore these fragmented tracks. They're heading out of the barrel. To get an idea of how well the GNN can perform, I'm going to also show track ML scores obtained with these conditions. So we throw away any track that has less than 4 layer hits, and they should be adjacent. This is a fairly standard requirement in seeding, and I'll show it for also 5 non-duplicate layer hits. So the takeaway here is that if we apply dbScan on our triplet GNN, which has at least 4 hits on different layers and they're adjacent, we get a TrackML score of 0.916. If we place an even stronger requirement that there should be at least 5 adjacent hits, we get a TrackML score of 0.932. And I would call this a fair approach to the calculation, but it is certainly lacking some realistic elements. For example, the noise we have removed, and the adjacency condition is perhaps not totally realistic. But once we switch to our learned embedding, being able to handle non-adjacent hits, we believe we can soften this condition and still get quite a good TrackML score. So this is kind of emulating the whole detector, just using the barrel. And again, it's an early result. These were obtained in the last month or so, and we're trying to understand how to improve these 2 big holes of the embedding efficiency and the doublet efficiency. And of course, the winning score for TrackML challenge was 0.92. And the timing of that score, I believe, was around 8 minutes per event. And our technique is of the order of 5 seconds, with many optimizations that we can still make. So I'll just summarize with that our seeding pipeline is complete, and we're at the point of now trimming down and improving the timing. And there are many options to do that. For example, mixed precision, including more features, or doing hyperparameter optimization on the GNN architecture. And the track labeling section is early days, but we see very promising performance, even just in the barrel, once we improve the TrackML score with using a fairly defensible change in the conditions. And there are still many different graph neural network architectures that we are yet to try, and are being published every day. So thanks for that.
Thank you very much. That was a very nice and on time, clear talk. So raise your hands, clap. Andy, I see your hand raised.
Hi. Very nice. Do you hear me, guys? Is that okay?
Yes.
Yeah, I can hear.
Very nice to get the update talk from the Exatrack upscaling. Let's put it that way from the. So my question is the following: would your system be, like, let's say, even faster or easier to do if you had a pre-selection on which your graph network runs?
A pre-selection on which element of the graph network?
On feeding into the, because you need to make the connections, right? Feeding. I'll refer to a talk from yesterday. There was a dehashing technique shown that also on a GPU, within almost nanos, let's take milliseconds, you can divide your data set up into, let's say, 5,000 this example was 5,000 buckets that also gained as 90% seed purity, but the initial seeds are then basically contained in the single buckets of only 50, 60 hits. So you practically have an automatic parallelization. Could you run basically the graph network in these let's say little buckets, and would that make the complexity of the problem way smaller?
That's an interesting idea. So you're basically treating each bucket, which is kind of aggregating hits or seeds together, and treating each bucket as a node. Is that the idea?
Yes.
And then still applying the GNN to...
Yeah.
I think it's, in some way, it's kind of a sort of voxelization technique in a way, and part of the Exatrix group are working on this, but combining it with then a graph structure would be, I'm not sure if we've combined that particular set of ideas.
So we are actually looking for, because we are actually actively looking at some either clusterization or seed finding or approaches that we can run and try out in the pre-pulled buckets, that we can classify very quickly whether they have a good seed in there or not. And then from a pipeline standpoint of view, would be interesting what's the most efficient thing to run as an afterburner after you have already basically pulled out an interesting set of hits. So
I mean, certainly the GNN, the doublet and triplet GNNs can slot into other pipelines quite well, as long as you have some concept of how triplets are connected. That might be the tricky element. But I'd be very curious if you could send me maybe a bit more information on the idea that you have, because it could vastly improve the speed of this, or at least the memory usage of this.
I'll send you a link. Okay.
That'd be great. Thanks.
Okay, I see another hand raised from Paolo. Go ahead, Paolo.
I just wanted to follow up, Andy, I think this is something which we should definitely try. You will. I think there is some similarity with what Nick is going to talk about in partitioning an event in domains which are very likely to contain 1 or 2 or 3 tracks, but not a random set of bits. So I think that is, I think we should definitely look into that.
Yeah, we should try this, because I think that's, I mean, one of the core components of Sabrina's work, which Moritz showed yesterday. That this approximate nearest neighborhood technique is probably good enough and super fast to do this pre-selection, and you don't have to do it by hand. And then I think the interesting part is what then. So what do we run on top of that?
There's time for one more question.
Do watch Nick's talk. I'll just quickly say, do actually watch Nick's talk, because he is doing learn embedding on triplets themselves.
I have watched every talk so far.
Good. Don't stop now.
And I watched Moritz talk, by the way.
Okay, I don't see another hand raised, and we should move on. So thank you very much again.
Thanks.
And let's keep going.